I really don't know. But like they had like angle
Oh,
them
it's that?
and like take the.
Yeah,
I don't remember what the unit was, but when they had to record the data for like however so many seconds, they had like 5 something bytes. It was like bigger than a like significantly bigger than a terabyte. They said it was like the equivalent of like 5 million MP3s or something.
Black holes are freaky. I don't understand
It was
them.
interesting.
This one's bigger than apparently Neptune's orbit around the sun, which takes 200 years to complete.
Happy birthday, Shane.
Happy birthday!
Thank you.
Hey, it wasn't me, it was Dan.
Did you like the fish?
Yes. I do.
Yeah,
Very
that's
good.
definitely something I would do.
Really?
Sounds like something Dan would do.
I wanna go for you.
How's your birthday going?
Good. You just woke up.
Tough ground.
We keep our sugars away from base. That is an alpha hydrogen. Is the carbonyl one position away? There's a hydrogen on that carbon, therefore that hydrogen is a little bit acidic. Put it in base, I can enolize that position and make this enol. There's the ene, there's the ol. So I have an enol here, which of course can reform to make the aldehyde. But it's not just an enol, because I've got the enol this way, but I've also got the enol that way. This is an enediol, which means once you've made that enol, it could rectify itself and go into the keto form. This way. And you just took your glucose, which was an aldose. And because it's an aldose, has an aldehyde group, and therefore can be oxidized, and therefore is a reducing sugar, and turn it into fructose, which is not an aldose, it's a ketose. Because it's a ketone, it cannot be oxidized, therefore it cannot reduce its surroundings, and therefore this is a non-reducing sugar. Which is why tolerance test tests positive for aldehydes, not for ketones, but tolerance test tests positive for both aldoses and ketoses, because ammoniacal silver nitrate is in base. And base makes your ketones turn into aldehydes. Yeah.
So these are all in equilibrium though, right? So that ketone could go back to
Yeah.
glucose.
Yep.
Is that why we can turn the ketones into
Mm-hmm.
sugar?
Yes.
Keto diet?
Yeah. got this. Okay, turning to that. And then it's anyone's guess. Does he go back to this or does he go over to that? So, like, the genie's out of the bottle now. You can't fix it. So that's a bad thing. And that's a bad thing down to the level of keep your sugars away from base, which means things like, how do you wash your glassware? Because detergents are basic. Soap is basic. And if you've washed your glassware with soap, and then you perform a sugar experiment in that glassware, you just threw all that money away. You just threw it all away. So you have to acid rinse your glassware. You have to be really, really careful if you're working in a sugar lab. You have to be really careful about what you're up to. Okay. This process from here to here is called epimerization, because you're taking this and you're turning it into that, and they are epimers of one another. Not technically, they're not, because epimers are different at one of the chirality centers, but you get the point.
I have a question.
Yeah.
To make it a sugar, does each like carbon have to be chiral, except for like the terminal ones?
Say again?
So like my question is, I guess can a sugar be like hydroxy groups on both ends of a carbon, or would it, since it's not chiral, that wouldn't be a sugar anymore?
I have a carbon here.
Mm.
Okay, you want me to put
Yeah.
an OH here?
Yeah.
An OH there.
The carbonyls above it.
Oh, like this?
Yeah.
That's not chiral. I would still need a primary alcohol here. This would be not a sugar, because now my number of hydrates per carbon is too high. I'm looking for the number of OHs and Hs to equal for every carbon.
Okay.
So epimerization actually will raise its head this way if I'll show you a real epimerization. If I had glucose, left, left, right, right, left, right, and I was stupid enough to put it into base, and it enolizes. Right, right, left. Okay. And then I reverse that, and I turn this back into an aldehyde. Carbon 2 here is chiral. Carbon 2 here is not chiral, but it's going to be. Carbon 2 is prochiral. So when you make your enol go back, even though it went back this time as an aldehyde, here you go. Right, right, left. I also get the possibility of this. strictly is epimerization. This is mannose. So I'm dumb enough to put my glucose solution into a flask that I scrupulously washed clean with detergent. That glassware is now basic. It makes an enediol. That enediol can reform as my original glucose, or as a fructose, or as a mannose. I just made a huge mistake. Okay. Keep them away from bases. Let's look at a couple of reactions. No mechanism for this, just a list. This is a chain elongation named after Fisher and Kiliani. This is an aldopentose. There's an aldehyde group, therefore it's an aldose. It has 5 carbons, so it's pentose. This particular one is ribose. And because it's a D sugar, because of that bottommost chirality center, this is D-ribose. All right, I'm going to add cyanide to this in acidic solution. Cyanide, no mechanism. I'm actually going to do it in the top, because that will show you what it's going to do. We'll do a nucleophilic addition. Okay? That's a nucleophilic addition. Cyanide sticks on the top, and then this group that was my aldehyde is now an alcohol. There it is. And you can see the elephant in the room. That carbon is not chiral. But that one is. This aldehyde, prochiral aldehyde, opens up. There is no rule that says that the alcohol single bond to oxygen that gets made here has to be on the right or on the left. So you make both. You make both. You make some of that, and you make some of this. Can you see what this is going to go on and be? This is going to be allose. And this is going to be altrose. All I'm going to do is now hydrolyze that nitrile down to being a carboxylic acid. And that happens in 2 steps. Actually, I'm not going to do it to the carboxylic acid, I'm going to do it to the aldehyde. That happens in 2 steps. First of all, I do a partial reduction. This barium sulfate. This poisons that catalyst and makes it not good at doing its job. This is a partial reduction of my nitrile. Something else. Let's see if we recognize what this is. What class of functional group is that at the top of the molecule? Anybody?
Is it a me?
Pronounce it more.
Imine.
Carbon to nitrogen double bond means that is an imine.
How can I have low battery? You charged all night.
I think my phone is on the way out. All right, that's an imine, and if you hydrolyze the imine, here's just dilute acid hydrolysis. I can make the aldehyde from that. There you go. I make the allose. And I make the outros. That's quite useful, to be able to jump from one class of sugar into another class. That's a pretty good thing. Let's do it backwards. Let's start with the sugar that is longer than I need and end up taking a carbon off it. So I could take that aldose or my allose and turn it back into ribose. The reverse reaction is called a rough degradation. And rough degradations look like this. This one's a little bit more complicated in terms of what the underlying chemistry is, because there's a radical in here somewhere, and we don't want to be writing any more radical stuff out. All right, it starts with this. That's the first step. Here's my aldohexose. And I've turned my aldohexose into the aldonic acid. For the aldose, and we've got this one is the hexose. we hinted at but didn't show it, that carboxylic acids can be decarbonylated. We can actually take off a carbon dioxide and make it flow away. What would be our reagent in here for this first step? Aldose to aldonic acid.
For potassium for or potassium
No, that's very, very strong.
lithium barium.
No, that would be a reduction. This is an oxidation, and I'm not touching this bottom primary alcohol. That would be slightly sensitive to oxidation. The aldehyde is very sensitive to oxidation, so this is a mild oxidation of an aldose to an aldonic acid. We did it on Monday. What's my reagent here?
Bromine water.
Yeah. What I'm going to do next is dimerize this thing by neutralizing it with calcium hydroxide. That puts everything here. Two of those, and then there's a calcium 2+ outside. And the calcium sits here in the middle between two carboxylic acid conjugate bases, two carboxylates. And that's going to allow me to lose the carbon dioxide. This particular step is tricky, and we're definitely not going to show the mechanism for it. This is going to use hydrogen peroxide and an iron catalyst. It is a radical reaction of some description. And it's going to chop the top part of my molecule off. This is why we read them from the bottom up. That part is going to be lost right here. So this carbon now gets to be the carbonyl. We read them from the bottom up so that we can see what the relationship between those hydroxy groups is on the way up. And my altrose just got converted back into ribose. All right, next. The remainder is going to be kind of skill building. We're going to show you how to draw some stuff. It's going to be a full page. You are going to cram a lot of diagrams onto the same page. Don't think that you can start this halfway down where you already are. Okay. What's that?
That's an aldehyde.
That's an aldehyde. What's this?
Alcohol.
That's an alcohol. What do alcohols and aldehydes do when they encounter each other? In the absence of base?
Carboxyl.
Nope. What types of reactions do aldehydes do? They're with electrophiles and nucleophiles.
Well, they're nucleophile.
Okay, do they react by substitution or addition?
Addition.
So their reaction is a...
Nucleophilic addition.
So let's do the nucleophilic addition of this. Can you see the nucleophile?
Yeah.
Can you see the nucleophile? What do I make?
Oh, hemiacetate.
What is that? That's a hemiacetate. Okay. The page is this wide, I'm starting in the middle. I'm going to use a lot of space. This is a Fischer projection of an aldohexose. This is a Fischer projection of D-glucose. Now, D-glucose is numbered this way. 1, 2, 3, 4, 5, and 6. Carbon number 1 is an aldehyde. Reaction is going to come to it because it has a carbon to oxygen double bond, and the carbon is on the losing end of the polarity of that bond, making the carbon our electrophile. There are nucleophiles all over this molecule. Nucleophile right there. Can I, do you think, take this lone pair of electrons and give them to that carbon so that it opens up? Who thinks yes? Show of hands. Yes. Who thinks no? Why do you think yes? Why do you think no?
Because they would have to go through the second carbon to go up to that carbon. No,
Okay, and
just doesn't seem likely.
what shape have I just made?
Try.
It's a triangle. Isn't that a bit strained? Not going to make a triangle. What else am I not going to make?
A square.
I'm also not going to make squares. So from carbon number 2, make a triangle. From carbon number 3, I would make a square. This is going to be a big no. It's going to be a big, big, big no for me. However, if I do it from carbon number 5, oxygen here, I just made a pentagon. Pentagons are going to go on the right-hand side of the page. Hexagons are going to go on the right-hand side of the page. Did I say right when I said meant left?
No,
Okay.
You said pentagons are going to the right and one to the left.
Yeah.
You said one thing, then another.
Pentagons go here. Hexagons go here. Okay. The first thing we're going to do is write this out again as a Fisher projection, but looped around. So carbon number 6 is not involved. Carbon number 5 is not involved. Carbon number 4 takes its oxygen and pushes it into the top of the molecule. Carbon number 3 just stays doing what it's doing. Carbon number 2 stays doing what it's doing. Carbon number 1 used to be an aldehyde. But it now is a secondary alcohol. And it could be on the left or it could be on the right. It's now a hemiacetal. So I'm going to write one on the left and then one on the right. Carbon number 1 is no longer an aldehyde. It is now, look at it, a hemiacetal. It has a hydrogen, an alcohol, and then an ether group. Okay. I'm going to point at what I have not done. Pay attention. This oxygen, carbon 4, is bonded to an oxygen, which is now bonded to carbon number 1. I did not do this. Because every time a line meets an angle, that means there's a carbon there. And there are no carbons here. Which is why I didn't do it. That line curves. This is one possible isomer. The other possible isomer carbon number 1 was an aldehyde. Aldehydes are pro-chiral. They're not chiral yet. But when you do reactions to them, like nucleophilic additions, the products become chiral. So carbon number 1 has the possibility of the alcohol being on the right or on the left. This is a Fisher projection. We know Fisher projections. I'm going to redraw that Fisher projection as a real pentagon in something called a Haworth projection. Haworth is not a word that exactly is pronounced the way that it looks. It's more like how-earth. In a Haworth projection, we write our pentagons this way. oxygen that is part of the hemiacetal being here at the 12 o'clock position. You can, if you're feeling adventurous, show that that oxygen is at the back of the molecule by making wedge bonds come out this way. And then we draw everything that dangles off these carbons as vertical lines. If your group is on the right-hand side of a Fisher projection, they point down in a Haworth projection. Okay. And we're going to go around this ring and label everything. It would be unwise of you to attempt to do this without labeling the carbons all the way from the beginning. This gets to be number 1, number 2, number 3, number 4. Number 5 is going to go here, and number 6 is going to go there. Because 5 and 6 aren't in the ring. Okay, look at carbon number 1. In this Fisher projection for carbon number 1, the alcohol is to the right. It's pointing down. The hydrogen is pointing up. At carbon number 2, the alcohol is on the right. That means it points down in the Haworth projection. Carbon number 3, that alcohol is on the left. Therefore, it points this way. Carbon number 4 is part of the ring. There it is. It's part of the ring. And then 5 and 6 dangle off it, and we kind of lose interest in the chirality of the side groups. We're really interested in what the chirality of the groups are in the ring. Once they're off in the side group, it's kind of lost. If we do it for this one, everything is the same. That's the same, that's the same, that's the same, that's the same, that's the same. The only thing that's different is carbon number 1. And in carbon number 1, my alcohol is now to the left, which means it points up. But everything else is the same. My sugar is still glucose. It is still a D sugar. However, it is now a 5-membered ring. And 5-membered rings are furanoses. Remember furan? Furan is the oxygen equivalent of pyrrole, 5-membered ring. This gets to be D-glucofuranosis. This gets to be D, glucofuranose. But they're isomers of each other, only at carbon number 1. Carbon number 1 is a special carbon. It is called the anomeric carbon because it is the only carbon bonded to oxygen 2 times. In the free aldose, it has a carbonyl. That is a carbon bonded to an oxygen 2 times. When you turn it into the hemiacetal form, carbon number 1 is holding on to an alcohol. That's 1 bond to an oxygen. And then to this ether. It's the only carbon in the sugar that is holding on to 2 oxygens. That's the anomeric carbon. So these 2 isomers of each other are anomers. If the alcohol at the carbon that is anomeric is pointing down, that is the alpha isomer. If the alcohol that is on the anomeric carbon is pointing up, that is the beta isomer. Beta is up, alpha is down. Okay? Let's do it for the hexagons. Primary alcohol stays the same. The oxygen on carbon number 5 is going to make a ether. Carbon number 4 is untouched. Carbon number 3 is untouched. Carbon number 2 is untouched. Carbon number 1 can go left or right. Gives me these 2 Fischer projections that differ only at carbon number 1. And again, you would be foolish not to number these. Going to redraw those as Haworth projections. Now in a Haworth projection for a hexagon, we write the hexagons flat, not standing on their point like we do for benzenes. These sit on the flat edge, and an oxygen in a 6-membered ring is a piran. So the right-hand side of our sketch are the pyranoses, left hand are the furanoses. Again, we represent everything that dangles off this sugar as being either directly up or directly down. And if your group is on the right-hand side of the Fischer projection, it will be pointing down in the Haworth projection.